Hi everybody, hope you're doing well. In this lecture we'll discuss rotation group and its representations. First, I will comment some preliminaries on group theory and on continuous groups, and it will not be a rigorous treatment of all the subjects because it's beyond the scope of our course. But you already know that in quantum mechanics, linear transformations are very relevant, and the parameters of the transformations may be continuous for some of the transformations you're working with. So for example, as an example, suppose you want to transform some coordinate system x and y to some x prime and y primed. It is a linear transformation. Okay, there are other transformations which are not linear, but in general we are discussing linear transformations. Rotation is a linear transformation for the matter, and a, b, c, and d are the parameters of the transformation. So x prime is equal to a times x plus b times y, and the set of matrices containing the parameters a, b, c, and d do form a group. They satisfy all the properties of a group, all right? But this is a general transformation here. I'm just putting some example with two components here. They could be components of a vector or anything, but just an example of a linear transformation, all right? A, B, C, and D do not depend on x and y. They are linear, they are independent coefficients, and they assume, suppose, values on real numbers. All right, so they are continuous. They are continuous variables. And there is a parameter space when dealing with linear transformations, which is the set of parameters you need to describe the transformation, and the dimensionality or the number of the number of parameters do you need to make the transformation corresponds to the dimensionality of the parameter space. All right, so the parameter space we are dealing with is finite. All right, we are discussing a finite number of parameters in the transformation. All right, to give another concrete example, suppose a rotation in the plane. All right, if you rotate an object in just two dimensions, your parameter space is one dimensional because you need only the rotation angle. But notice that the angle of rotation is a continuous parameter because you can rotate from 0 to 2 pi or even more, because the object can be rotating, and it is continuous. All right, so in the parameter space, rotations in two dimensions are described by only one parameter, so the parameter space is one dimensional. But if you are talking about three-dimensional rotations, you need describe, or you need to specify the direction of rotation and the angle of rotation. All right, or in three dimensions you need to specify angles, two angles, because the direction is a unitary vector, so angles of this direction of rotation and how many degrees you will rotate the object. All right, so in three dimensions your parameter space would be three-dimensional because you need three angles of rotation: the rotational around the x-axis, the rotation angle around the y-axis, and around the z-axis. All right, if you want to specify that way. Well, among all the continuous groups, there are specific, 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 type, kind of object which is called a Lie group. Okay, Lie groups are very important in quantum mechanics, right? Lie groups we will discuss in brief, but rotation groups are uh, special kinds of Lie groups, all right? So they are they were studied first by a Norwegian mathematician called whose name was Sophus Lie around this year, right? And a Lie group is related to it is the Lie group. A Lie group is related to infinitesimal transformations around the identity. If your transformation can be as small as you want and it is close to the identity, which corresponds to do not transform anything, you're talking about the Lie group. So related to they are groups related to infinitesimal and continuous transformations, linear transformations, of course, in our case, in the neighborhood of the identity, right? So there is an infinite set of elements because supposing a unitary transformation, your transformation will look like this object, the identity, plus some, it must be unitary, some Hermitian operator here, and this is the imaginary unit, some G here, which is a matrix, times some epsilon, and this epsilon can be done infinitesimal, all right, so close to zero. This type of transformation, this kind of transformation are related to groups which are called Lie groups, all right? And in Lie groups, there is a specific algebra for that specific group, all right? If you consider, for instance, in quantum mechanics, notice the following. Suppose you have a ket vector psi, which you want to calculate after the transformation from a unitary transformation applied to your object, the untransformed, the original object. So you are applying a transformation, a linear transformation, to a vector, which is a complex vector in Hilbert space, and you are finding your transformed object, which is psi of some epsilon, some infinitesimal epsilon. So this is what we can call the psi primed. And in this case, we have the psi of epsilon is equal to the identity times the imaginary, some matrix G, which is this matrix here is called the generator. So there are generators of the transformation. They are matrices when dealing with the matrix representation. They are the matrices responsible for or inducing, generating the transformation, right? Generating the transformation. So these matrices here, the unitary matrices, producing some transformation in your vector here, which is a complex vector in general, produce another vector in Hilbert space in the case of quantum mechanics, and these matrices here, which produce the transformation, are called the generators of the transformation. Right? So if you are writing things like this, apply to the psi, the original psi, right? You can make an expansion of this transformation around the identity, all right? So Lie groups are groups which are concerned with transformations, infinitesimal transformations in the neighborhood of the identity. So you could just write this as u of 0, no transformations, times psi of 0, which is the original object, plus the derivative of the transformation with respect to the epsilon times epsilon times the original object. So Lie groups must be composed of a set of elements. There are infinite elements because this u here you can make it infinitesimal, but in the end you'll make finite transformations and you will have a set of infinite number of elements taking on continuous parameters theta in place of some epsilon here. And in this case, you need to be able to calculate the derivative. So Lie groups are smooth and act on differentiable functions. All right. So this is another property. So the matrices generating the transformation are called generators. And notice here that if you connect the two expressions here, you'll find out that du d epsilon just corresponds, which is a matrix, to I times G, all right, times this matrix G here, all right? And notice if you differentiate the operator here, you'll find this. And of course, the psi prime minus the psi at 0 epsilon, this change in the vector is just the derivative of the transformation matrix, which is I times G times the epsilon, which is infinitesimal, of course, times the original object. So this is the delta. This is the delta of the transformation. And this is a very interesting relation here. Okay, so the delta psi corresponds to the derivative of the operator transforming times an infinitesimal epsilon times the original. So your transformed object is, of course, nearly parallel for an infinitesimal transformation. If you will think this as a vector in Hilbert space, you are just considering the object, the transformed object, say this object, forming an angle epsilon, which is close to 0. So they are nearly parallel after the transformation. The psi prime and the psi are nearly parallel. Okay, but of course you can expand the transformation around some epsilon in more terms in the series. All right, but the linear expansion goes to this term here. All right. Well, another important property is, well, first let me say something. How many generators I guess the general linear groups are called the GL of dimension n, which specifies the dimension of the parameter space, all right? So G for general linear transformations, and n is the dimensionality. So how many generators? You have number of parameters, which is the dimension of the parameter space, will correspond to the number of generators in the group. All right, this is what we have. So as an example, again, take rotations in 3 dimensions. You need to specify a unit vector and an angle, and this unit vector specifies a direction, so it has a constraint because the direction implies that the unit vector is n dot n equals to 1, so the scalar product with itself is 1, and in this case you have just two free parameters in n and the angle of rotation, so there are 3 parameters. Or if you prefer, you can specify some theta x, theta y, and theta z. There are 3 parameters. So there are 3 generators because the parameter space corresponds to 3 angles, or one unit vector which has just 2 free parameters and 1 angle of rotation. So 3 generators in this case. Remember that when dealing with the rotations of a spin half system, there are 3 Pauli matrices, and the Pauli matrices are the generators of rotation, right? The operators for instance, if you consider spin half, your unitary matrices will be of the form minus I, some sigma vector dot n, theta over 2. So notice there are 3 matrices here. These are the generators of your transformation. In an infinitesimal situation, it will look like 1, the identity matrix, minus I, some sigma x theta x, which is infinitesimal, so I will replace by some epsilon x, minus I some sigma y epsilon y, minus I some sigma z epsilon z. All right, for an infinitesimal transformation, you'll have 3 infinitesimals, and the generators are the matrices sigma x, sigma y, sigma z, and these matrices form an algebra. Right? So how many generators? You need to know how many parameters you need to perform the transformation. And of course, there will be a set of n matrices with dimension, with that dimension, of course, with the dimension of your representation. Sorry, right? So for a general group, how many generators? The answer is how many parameters do you need? And you need to specify then some transformation by the following form. In infinitesimal transformation by an angle epsilon, you'll have an epsilon 1, epsilon 2, till you reach the end component of this, say vector epsilon, all right? It's an infinitesimal vector. You will be approximately given by the identity plus some summation over j equals to 1 from 1 to n generators times the infinitesimals. All right. So this will be matrices, and this will be infinitesimals in general. Now let us consider some aspects of Lie groups which also apply to rotation group. All right. Suppose you have, for knowing a group, you need to have U1 times U2, a first transformation, a second transformation must correspond to a third transformation, which is also contained in the set of the group. Of course, you must have the property of associativity as for any group. So you don't need to specify what to do first. You cannot reverse the order in general, but you don't need to specify multiply this by this first and then that, or this and this first and then that. Just keep the order, but you can make this first or this first, the result is the same. So this is associativity. The product of two transformations is another transformation. It pertains to the same set of transformations. Any transformation has an inverse. Okay, this is the identity. And of course, if you multiply the identity by the transformation, it is the same as the transformation times the identity, and it is just the transformation you want to do. So there is an element of identity. Lie groups are concerned with transformations in the nearby of this identity here, right? So any group needs to satisfy all these properties. Keep that in mind, right? Well, so let us specify some two infinitesimal transformations in a group which has n generators. The first will be this one, the identity plus some G alpha. Alpha can be anything. Imaginary here. I forgot I was forgetting the imaginary unit here because matrices must be unitary in these representations, and G usually they are Hermitian. Okay, they are Hermitian. So suppose a transformation around the axis alpha. I will say axis, okay, so the direction of alpha by an angle epsilon. I could use some epsilon 1 here, okay, epsilon 1. So epsilon 1. Of course, I can go to higher order. So the next term will be minus 1/2 of minus, because this is squared, you get a minus 1. So the G alpha squared, epsilon 1 squared. And of course, I can perform a second transformation by another axis, say some beta axis, okay, by an angle epsilon 2. So we'll have something like this, epsilon 2 squared. Of course, I will retain only first order, and I will make it doesn't change the generality here. I will make epsilon 1 is equal to epsilon 2 some epsilon. All right, suppose that you can do the calculations using distinct epsilons. It doesn't matter because we are dealing with infinitesimals. So if you make a transformation, remember you apply a transformation to an object, the matrices of transformation to an object here, and this is a vector in Hilbert space. But I will just consider this order of operations. So in this order, the transformation 2 acts first, and the transformation 1 acts after the first transformation was performed. All right, so the calculation, neglecting here the second order terms, it will not influence what I am willing to show you. All right, but if you can plug all the orders. All right, the correct calculations is to take the second order also. All right, but they are in the square of the operators here or the matrices. I am not interested in the square. I'm interested in products. So here, notice that I have for the first transformation this kind of thing. I am using epsilon1 equals to epsilon, all right? And the second transformation is 1 plus I g beta epsilon, the same epsilon. The alpha and beta can be distinct. They do not need to be the same, all right? And in this case, if they are distinct, suppose they are distinct, you'll find out 1 plus I g alpha plus g beta times epsilon, and this product must be performed in this order: g alpha, g beta, epsilon squared. All right. Of course, if you keep these parameters to order of epsilon squared, you have a minus 1/2 of g alpha squared plus g beta squared epsilon squared. All right. But what is our main concern is this term here. All right. Notice that I can perform the calculation in the reverse order. So it corresponds to applying the transformation 1 first and then the second, all right, in this order. And we'll find out, if you do the math, you'll find out 1 is just reversing alpha and beta, is just that, plus I, g beta plus g alpha, epsilon, minus g beta g alpha epsilon squared, and that term is the same. You can reverse the orders here, no problem. If you plug in this term here and this term there, okay, so we'll find out something like that. Notice the following. Notice the following. This summation of matrices, you can reverse the order because the addition of matrices is a commutative algebra. All right, so you can add matrix A to B or B to A, and this is a commutative operation. So the non-commuting aspect is not in the linear order. Okay, you can reverse the operation. If you reverse the order of the operation, it is commutative to first order in epsilon. Okay, in epsilon it is to first order, it is commutative. You don't need to worry about commutativity to first order. But notice that in second order, that term is also commutative, so that's why I'm not worried about these factors here. But these terms, which comes from the product, all right, they are, when you apply this order of operation, they are multiplied as g alpha times g beta. And if you reverse the order, you have g beta times g alpha. And now you can calculate the commutator. Okay? Now you can calculate the commutator. So commutator of two transformations in the Lie group, all right? You'll find out that you have u1, u2 minus u2, u1, and you must subtract these two operations. Notice the identity is removed. The first order term is removed. That term is also removed if alpha is equal to beta. But now you have this commutator here because you have minus g alpha g beta times epsilon squared and minus that minus here plus g beta g alpha epsilon squared. And this is just minus epsilon squared commutator of two generators of the group. Okay, this is very important. Another important aspect is that if you look at, I'll leave that operation here, all right? If you look at this thing and you have a finite number of matrices in the set of generators, the product of two generators must be a third generator. Otherwise, your parameter space would not be finite, which is the assumption at first, I guess. So you will produce another generator and you would need another parameter. So if the dimensionality of the parameter space is finite, you need to have a finite set of generators, and the product of two generators must be in the set. Otherwise, you will not you will not satisfy all the properties of a group. So this product here must be some g lambda, proportional to some g lambda. You cannot have another thing which is not in the set of generators. So it can be a distinct matrix, but must be a generator, all right? Then when you calculate the commutator here, G alpha and G beta, you have G alpha, G beta minus G beta, G alpha, and this must be proportional to some other lambda matrix, which is another generator. And usually it is defined by an imaginary unit and some function here, f. Okay, this f depends on alpha, beta, and is summed over lambda. Okay, is dummy index here, you must sum over lambda. All right. So this is called the Lie algebra of the group. Okay, this is the Lie algebra of the group, and this f, alpha, beta, lambda are called the structure constants. They are constants of the group. Okay, so this is it for Lie groups. Now we can provide an example, a clear example. Well, first let me just say another thing. If the generators in a group all commute with each other for all the alphas and betas here, if this applies, you are talking about an abelian group or commutative group. But otherwise, if they do not commute, they have structure constants which are non-vanishing for some alpha, beta, and lambda. Okay, some of them may be zero, but not all. If just for one pair of alpha and beta, they do not commute, you have a non-abelian group or a non-commutative group. All right, this is very important. There are applications in particle physics and in quantum mechanics of abelian groups and non-abelian groups, but perhaps for modern theories of elementary particles, non-abelian groups, which are related to Young-Mills theories, are very, very, very important. Okay, so you need to remember that if the generators of a group do not commute, you are dealing with a non-abelian group. And as an example, polymatrices. This group formed by these kind of things, some theta and some direction. The elements of the group are given by this. Okay, generators are the Pauli matrices. Okay, this set of matrices, they are the generators of your group. And you have an algebra. Sigma sub I, sigma sub j is equal to twice imaginary unit ijk sigma k. All right, so the structure constants are twice the Levi-Civita tensor. All right, your structure constants are 2 epsilon ijk. All right, these are the structure constants. So the spin half is a non-abelian group. All right, it's a non-abelian group. Rotation groups, if you consider 2 dimensions, a rotation is abelian, is an abelian operation. But if you go to 3 or more dimensions, rotations are non-abelian operations because the order of the operations matter for the final result. And this is encoded in the Lie algebra of the group, in the Lie algebra of the generators of that kind of transformation. So in the case of this group, which is called the SU2 group, okay, the generators are non-commuting, and in this case is a non-abelian group. Of importance, in quantum mechanics, there are others, but of a very relevant aspect in quantum mechanics, you can consider the unitary groups, UN. So the UN are groups of matrices composed by matrices of dimension n, and they satisfy a property u dagger is equal to u dagger u. So the inverse is usually the inverse. The inverse is the transpose conjugated or the complex Hermitian. But here, in general, you have the determinant of the matrices equal to 1, the modulus. All right? If you pick some part of the group, a subgroup, you'll find out the special group, special unitary group, the SU with dimension n. All right? So the special unitary whose matrices representing the generators has dimension n. Okay, so the SU2 are the generators of the SU2 are the Pauli matrices. They are 2 by 2 matrices. But you can find out other unitary groups which are the special group. But what defines this special group is that not only the modulus of the determinant is equal to 1. The determinant is plus 1. All right, the determinant is exactly equal to 1. Here you could, in the general case, you could have the determinant is equal to some phase. Okay, because the modulus of a phase is 1. All right, but in the particular case of a special unitary group, the determinant is exactly 1. Right, this defines special unitary groups. This puts some constraints on the generators of the group. All right, this is a very interesting aspect. It is a subgroup of this general group here, perhaps. Okay. Well, so far so good for Lie groups and Lie algebra. You can remember that just to discuss a little bit more about generators here. Evolution in time, okay? If you are concerned with time evolution, time evolution produces transformations, and these transformations correspond to evolution of states. If we are considering the Heisenberg, sorry, the Schrödinger picture here, and time evolution corresponds to this. The identity for an infinitesimal delta time, delta t, for an infinitesimal delta t, which is the epsilon here, all right, you will find out minus I divided by the h bar times the Hamiltonian delta t, all right? So notice the generator of time translation, because you're translating your system in time, is the Hamiltonian, all right? Spatial translations. You'll be something like this. U of some delta x in one dimension here. You'll have the identity and what carries a particle from one position to the other. Its velocity or its momentum if you are talking about quantum mechanics. So it could be something like this. Px times dx divided by the h bar, right? So this is what produces the partial translation of a function. So generators here are the momentum operators, all right? These are the generators for spatial translations. And what can be the generators of rotations? Okay, rotations. What are generators? We discuss a little bit more about that, but just a brief, just to remember, if you consider a sphere rotating, okay, a rotating sphere, it has some intrinsic angular momentum, which I'll call spin of that sphere. Think classically here, okay? A sphere rotating, this is the axis of rotation, some s here, and the modulus is proportional to some quantity, usually denoted by this capital I letter, and it's called the moment of inertia of the object, all right? I don't remember the formula for a sphere, all right? Sorry. I don't remember the formula, but you can find elsewhere. And it is proportional to the omega, which is the frequency of rotation of the object. All right. In this case, the vector can be calculated attributing to the omega some vector character. So if you consider a right-handed screw, you can rotate by the right hand convention. You can rotate, and rotation is in this plane here, in the plane. Rotation occurs in a plane, of course, and the vector perpendicular to the plane with using the rule of the right hand points upwards in my example here. So this is the omega vector. Okay, but if you consider just the modulus, it will be I omega, and this is I delta the angle. If you put a mark on the surface of the sphere, this mark will rotate. You can assign a vector here from the origin to the mark, and this vector will rotate with the mark, and the angle change here, if you look from above, you have something like this. This sphere is rotating, the mark is here, and this object is rotating here. Okay, you're looking from here, the object is rotating. So this object changes angle. This is the theta measured from some axis, say this is xy axis and this is y axis, and the delta theta, delta t corresponds to rotation. So delta theta, delta t is this frequency here. It's related to the intrinsic angular momentum. So intrinsic angular momentum in this case. And what produces rotation of the object? Angular momentum. So it generates rotations, okay? So what is generators for rotations? Angular momentum. Okay? This is what we need to know about. All right? So angular momentum is generator of rotations in classical mechanics and also in quantum mechanics. Now let us discuss a little bit more about what really matters, which is the rotation group. Okay, so rotations. Okay, let us consider a rotation of a vector. Suppose you have a vector v, and you want to calculate the new vector v primed, which is produced by a rotation around the z-axis on v. Okay, the original vector. There are two possibilities for considering rotations, which are the active viewpoint and the passive viewpoint. In the active viewpoint, you consider the coordinate system unchanged and the object rotates, okay, the vector rotates. And in the passive viewpoint, it is like you are moving with the vector and the coordinate system rotates in the reverse direction, okay? But we will adopt in here the convention of active rotation. We will rotate the vector and keep the coordinate system unchanged, all right? So you have an equation of this form, Vx prime, Vy primed, Vz primed must be represented by some matrix here, some components, and this is Vx, Vy, and Vz, the original vector here. You plug in the original vector, but you already know that if you rotate around the z-axis, suppose this is the z-axis, and you rotate this vector here around the z-axis, the z component do not get mixed with the other components. So the z component, when you rotate something around one axis, the component along that axis remains unchanged. Okay? So, of course, the components of that matrix must be in the following form because you are rotating along the z-axis, so the z component is kept fixed. So you do not mix z component with the other components. The same as if you are rotating along the x-axis, the x component is kept fixed. If you are rotating with respect to the y-axis, the y component is kept fixed. All right. And now we need to know what happens here for these elements. Let us try to figure out what they are. All right. Suppose this is the y-axis. We do not have to worry about the z component. It's just kept fixed. So we are considering the projected components of the vector in the xy plane, right? So z-axis is pointing towards for outside the board here, okay? So rotations in the positive sense is counterclockwise here, and it will be pointing the rotation along the z-axis, all right? So the z-axis corresponds to something going outward of the out of the plane of the board here. Okay. So if you have the vector v, I will write v, but remember they are the components y and x because the z component is is outside the plane, all right? It's perpendicular to the plane. So the v vector here, the original vector points here. If you rotate by some epsilon here, suppose an infinitesimal rotation, some epsilon rotation, you will have, I will exaggerate a little bit here, but you will have a v primed vector, which is rotated here. This angle of rotation is some epsilon, is infinitesimal. Okay, I don't know if you can see, it's an epsilon there. Okay, and notice that the original vector has some projection here, which is the Vx, and some projection here, which is Vy, okay, Vx and Vy, and rotated vector has some components Vx primed, Vy primed, all right? We are trying to connect the Vx primed and Vy primed with Vx and Vy and given the angle of rotation. Remember that rotations preserve norm. Okay, they preserve the norm of the objects. They rotations do not change the size of the object. The object remains at the same size. So this size is the same, which means the modulus of V is equal to the modulus of V primed. Is an important aspect of rotations. So this way you will have that the square root of the sums of the squares, okay, in the original vector or calculated with the new components, you'll get the same result. All right, vector, the size of the vector is not changed. But notice that if you rotate the v vector here, it corresponds to rotating this Vx component a little bit and rotating the Vy component a little bit. So I will consider this is the Vx. When you rotate a little bit, you'll find out some rotated Vx. Okay, I'll call this Vx2 prime. All right, it's rotated component of the x axis. And when you rotate this thing, because the vector is just the sum of the two components, the x and the y, if you rotate the vector, if you are rotating the vector here, you're making this thing here. You're rotating simultaneously the components by the same angle epsilon. So this is epsilon here, and the Vy component, when you rotate that, it also preserves the length. It will be V2, Vy2 prime here, and this is the same angle epsilon. But notice that this rotation of the component Vx produces a y component here. Produces a y component. And this component here is just the Vx, which is the same length here, and this is the Vx times the sine of epsilon. Okay, times the sine of epsilon. And the rotation of the y component produces a negative result because it points to the negative direction in the x-axis, but it produces here an x component which has the size of Vy times the sine of epsilon. All right, but sine of epsilon is nearly epsilon for small angles. All right, this is a property for infinitesimals. The cosine tends to unity and the sine tends to epsilon. So, of course, when you rotate by an infinitesimal, I can see that the Vx primed here corresponds to the original Vx, right? Corresponds to the original, but minus that small amount which is produced by the rotation of the y component. So this is minus Vy times epsilon. Sign of epsilon, but we are approximating by epsilon, all right? And the Vy primed here, the Vy primed is just the original Vy, but it increases because that amount gain that part which corresponds, which is a result of the rotation of the x component. So Vy plus Vx times the sine of epsilon, which is just epsilon. All right. So the Vy prime here is just the original plus that amount here. Okay. And the Vx prime, the transform, is just the original minus that quantity here. And this we can rewrite as a matrix. Look that the Vx prime is just 1 times Vx, okay, minus epsilon times Vy, minus epsilon here. And for the y component primed, we have a 1 times the Vy, the original, plus epsilon, epsilon times Vx. All right, so this is the rotation matrix we are talking about, a Z rotation matrix. All right, but notice this matrix here is the identity plus some small off-diagonal components. Of course, you can calculate second order perturbations here. You will find out some minus epsilon squared over 2, minus epsilon squared over 2. You'll hear nothing because you're rotating around the z-axis, okay? This keeps fixed. But if you are considering to first order in epsilon, this is the matrix of rotation, all right? Well, now you can, I hope you could understand what I was doing there. But now notice that I have found some RZ of epsilon matrix, which is just the identity, the ones in the diagonal, minus I epsilon and some generator, which I will call Jz divided by the h bar, because J is usually used for, it's customary to call the general angular momentum by this letter, this capital letter. And since this epsilon is a-dimensional and angular momentum has units of joules times second, which is the same as the Planck constant, we normalize by Planck constant in quantum mechanics. And this matrix is a-dimensional. So the Jz divided by the h bar is equal to, because remember, our matrix was this thing here. 1, 1, 1 in the diagonal plus epsilon. We have zeros in the diagonal because we just bring the ones of the diagonal to the identity matrix. And the off diagonal are proportional to epsilon. Here we had a -1, here we had a 1. So we can just now insert a minus I here and multiply here by I and here by I. Okay? Because minus I times I just recovers this plus sign we have here. This sign is now changed to a minus I, all right? But we just have to insert into the Jz divided by the h bar matrix the imaginary. So here we have imaginary minus 1 times imaginary, 0, 0, 0, 0, 0, 0. And in this way, the rotation around Z can be done by a unitary matrix. As a matter of fact, rotations in real rotations in R3 correspond to some matrices which are called orthogonal, special because the determinant is 1, orthogonal of 3-dimension matrices, special orthogonal matrices. And orthogonal matrices are the real version of unitary matrices, because an orthogonal matrix, the inverse is equal to the transposed. You don't need to complex conjugate orthogonal matrices because they are all real valued matrices. But we can map it to a unitary representation, and the unitary representation corresponds to this object here. All right? So now I can multiply everything by h bar here, and we have h bar here, h bar times this matrix is Jz. If you want to calculate the x component, you also get an h bar. The components in the x direction are unchanged. So notice that the unchanged components must have zeros in the generator. Okay, so x has zeros here because what connects the component x to the others must be zero. The x component of a vector is preserved in the rotation around the x-axis. So you find out 0 minus I, and 0. And you can, by the same procedure I did for x, y plane, you can do it for the YZ plane, which corresponds to x rotations. And you can do for the x and z plane, which corresponds to the y rotation. You'll find out the jy is just h bar times the z component, the y component gets zeros in the elements which would connect the y component of the vectors to the others. So what would do it for y component? You just put in zeros. And you'll find out some imaginary unit here minus the imaginary unit here and zeros in the diagonal. They are all traceless matrices. All right, this is a property of angular momentum. The generators are traceless matrices. It's a constraint of it. In the book of Sakurai, you can look at chapter 3. Okay, Sakurai, modern quantum mechanics. And there he discusses what is the result of doing some Rx, Ry, and reverse order. Okay, they do not commute. You can show that. But now you can calculate the Lie algebra of rotations. All right, you can calculate the Lie algebra. So you can, for instance, calculate Jx times Gy minus reverse order, and you'll find out, you can calculate that. It's just matrix multiplications. I will not do it here. You can do that. You'll find out I dh bar times the matrix generator which is missing. So xy minus yx is proportional to the z component. And if you do for all the multiplications possible, zx, zy, xy, and all that, you'll find out Lie algebra of rotations, algebra of the generators. Rotation generators, okay? Of rotation generators. There are three, because in three-dimensional space, which is the most important situation, there are three generators, Jx, Jy, J subindex Z, and this corresponds to the angular momentum, general angular momentum. They are the following. If you pick some alpha component, you commute it with the beta component, you'll find out imaginary h bar epsilon ijk or alpha beta lambda j lambda. So in the particular case, you will have this. Okay, this is a particular case. All right, and you can just make cyclic permutations here, x, y, and z, which is just encoded in this very general, where this epsilon here, this epsilon alpha, beta, lambda corresponds to the Levi-Civita, right? The permutation symbol. If you make cyclic permutations here, you can just do this the following, right? J equals to I, H bar, some other J. All right, you can just start from the Y here, Y, then you go to the Z, and then the result is the X component here. All right, so you can do cyclic, this cycle here, you can do cyclic permutations. All right, so X, Y, you get Z. Y, Z, you get X. Z, X, if you do Z, X, you will get the Y component of generators for rotations. So, what do you have? For three-dimensional vectors, you have a rotation group acting on vectors. So, rotation group acting on vectors V, which have vectors in three dimensions, three components. They are 3 by 3 matrices. They are orthogonal matrices, special orthogonal matrices, 3 by 3 matrices. But there are three angular momentum operators, which are the matrices we just have demonstrated or calculated here. But rotations must satisfy the following properties. A rotation 1 times a rotation 2 corresponds to a third rotation. Of course, we are dealing with matrix multiplication, and matrix multiplication is associative, so we do not have to worry about that. So that group property is already ensured by the usage of matrix algebra. So two rotations produces a third rotation. Any rotation has an inverse. So some R has an inverse, which gives rotation, gives you the identity, which corresponds to no rotation. All right, the identity of a rotation is no rotation. And of course, you have the identity. Okay, these are the most fundamental properties. Now we want to find out representations, matrix representations of group. Okay. of this group. And find out matrix representations, it corresponds to finding some homomorphisms with other groups. Okay, such that to every element of this group here, to every element on the special orthogonal in 3 dimensions, which is the group acting on real vectors in R3, corresponds an element in the representation. So in the representation, we need to have some B, which is the letter usually used to represent that this is a representation of the rotation group. Some D of that given rotation R1, just a matrix, not this matrix, another representation matrix, times R2. So this is a matrix representation representing this rotation here is equal to a matrix D of R3. So you need to map, okay? This element corresponds to R1, this element corresponds to R2, and that element corresponds to the resulting rotation. Of course, you'll have to have an inverse, which is the identity here, okay? And also d to the minus 1 of r is d to the r minus 1 is a property which is usually valid. And of course, there must be an identity, all right? So you need to map objects in a matrix representation with put into correspondence the objects. Why we need to do that? Because vectors in R3 are not the only objects we are concerned about in quantum mechanics. There are scalars, there are spinor, polyspinors, there are other objects, and I want to find out what a rotation. So what a rotation does, what a rotation produces in a physical state, which is an abstract object with dimension of the Hilbert space you are considering. Okay, so this object can be a Pauli spinor, so it has two complex components. It can be just a scalar, so in the Hilbert space concerning angular momentum, it has not intrinsic angular momentum. It can be a complex space with 3 components. It can be a complex space with 4 components. And this object, when you act with a rotation, which acts in a vector producing a group of rotations, there must be a representation, a matrix which acts on that object and also produce some mixing between the components of that object. But the components of this object are not directly related to the space as in the case of a real vector, because Vx is the component along the x-axis and Vy along the y-axis. But for a spinor, the up spin, down spin, there are two complex numbers. You cannot directly relate these things to the space dimensions or the coordinate space. All right. So you need to find a representation for a two-dimensional Hilbert space. you need to find out matrices, this D here, matrices which are 2 by 2 instead of the original group. So you need to find a mapping, okay? In this case, you are trying to find out a mapping, a homomorphism, okay? And of course, there is a trivial representation. A trivial representation corresponds to replacing any rotation around any direction at any kind of rotation by one. This d of r is one, number one. Okay? So you rotate a vector, v prime is equal to the rotation times v, you rotate a vector, and in this representation you have an object, phi prime is equal to 1 times phi, which is exactly phi. The object is unchanged by rotation. What is unchanged by rotations? Scalars. So this is a scalar field. It can be real, it can be complex, real or complex. For quantum fields, it has some importance because real fields are chargeless and complex fields are charged under certain interactions. Okay, but scalar field are a trivial representation. A scalar field has no intrinsic angular momentum. A scalar particle can have a orbital angular momentum, but there is no such thing as an internal degree of freedom. So the spin of this particle, spin, is said to be spin zero. Okay, spin zero scalar corresponds to replacing any matrix by one. Okay, matrix act on a vector, a 3 by 3 matrix acting on a vector. If you rotate a vector, what happens to a scalar? Nothing. A scalar is a scalar, it is unchanged by rotations, and in this case, it is a scalar field. Okay, so this is the dimension one, matrix one by one, just the number one, okay? But now I can find another representation, and the even dimensions are called the Spinard representations. So spin half representation. If you rotate the vector here, if you rotate the vector here, what happens to a polyspinor, which has two components, the up and down state? You have to calculate using some matrix, a 2 by 2 matrix, applied to some psi up and psi down, which is just the original state psi here. So what does that rotation applied to a vector does for a spinor, a Pauli spinor? Okay, so you have to find out matrix representations of that rotation by given n and given the direction given theta, and this is just the exponential of minus I, the direction dot with the Pauli matrices, the theta angle divided by 2. This is the representation. And you need to find out an exact correspondence of, in this case, of the angular momentum with the algebra. And the algebra here, if you define h bar over 2, the vector here, they are matrices here, but represent as a vector, h bar over 2 sigma the algebra of the sigmas just emulate the algebra of angular momentum. And this is called the spin half representation. These matrices are unitary. They are special because the determinant is 1. And this group is called the SU2 group. Okay? This is the SU2 group. Well, and you can go on, find out these are 2 by 2 matrices. In this case, 2 by 2 matrices. And this is spin 1/2. Spin 1/2. Okay? And you can go on and find out a representation which is the original representation, which corresponds to a vector field. So the proper representation is vector field. So spin 1, vector field. And you can go on spin 3/2, spin 2, and you can proceed further. All right? You can find out matrices, and usually the groups representing rotations are the SUN. So the most or another groups of SO, and also there are some representations. Okay, but concerning the spin is an intrinsic property. So spin in the context of quantum mechanics, intrinsic property of a quantum particle, but because particles are represented by fields in quantum mechanics, I can call it the field, right? Intrinsic property of quantum field related to intrinsic angular momentum. All right? So it is intrinsic angular momentum. And from where they come from, these properties? It comes from representations of the rotation group in 3 dimensions, which we are concerned about here. Okay, so they say somebody said sometime that what is not forbidden is compulsory. So if you have rotations and you have the possibility to construct objects, scalars, complex with 2 components, complex vectors with 2 components in Hilbert space, complex vectors with 3 components, complex vectors with more components, why not? So in nature, these objects will show up, will appear. And in this case, all right, we have the following properties. So we have integer spins, okay? We have half integers, okay? These are the 2 possibilities for representations using the SUN groups. And in this case, there are scalars, vector fields, tensor fields of rank 2. Okay, here you'll have a 1/2 field, a 3/2 field, and you can go on forever. 5/2. Okay, you can go on. So the SZ projection, which is usually the component which you measure, the SZ component divided by the H bar. In any case, okay, the SZ component divided by the H bar is always ranging from -s minus s plus 1, till you get to s. So in this case of a spin 0 particle, there is only one possibility of projection, 0. The particle has no intrinsic spin. For spin 1 particle, you have three possibilities for the components, minus 1, 0, and 1. For the spin 2, you will have minus 2, minus 1, 0, 1, and 2. Okay, you have these possible projections. So in the case of half integer spins, for spin half, you will have minus 1 half plus 1 half. Because you start with minus s minus 1 half minus s plus 1 half, you just arrived at the maximum possibility, all right? So here you'll find out minus 3 halves, minus 1 half. You keep adding 1 till you get to this number here. 1 half, 3 halves. So notice that you have 2 by 2 matrices here, 2 by 2, 4 by 4, 6 by 6 for the case of 5 halves. Here you have one-dimensional matrices, just the number 1, okay, for representing rotations. 3 by 3 matrices, 5 by 5 matrices, here representing the spin 2 particles. And in general, the representation will have the dimensionality n is equal to 2 times s plus 1. All right, so 0, dimension 1, 1, 3, 2, you get 5. 1 half, you get the dimension of the matrices, which is 2. For 3 halves, you have 4 by 4. So the dimension of the generators, so the generators are Jx, Jy, and Jz, which is just now represented by a spin, Sx, Sy, Sz, all right? These matrices will be represented by n matrices, all right? So this is what we are talking about, the dimensionality of the generators, okay? And the parameter space is also, in this case, when we are concerned about just spatial rotations, the parameter space is three-dimensional, but the dimensionality of the matrix representing the group is connected to the spins, okay? And in next lectures, we'll find out, we'll discuss, to be precise, we will discuss the connection between quantum statistics and spin, which is called the spin statistics theorem. And it's a very important thing, because half integer spins behave one way, integer spins behave in another way, this distinct behavior, all right? But just to give you some examples, spin 0 particle, you can consider Higgs boson. It's a spin 0 particle, is a scalar field under rotations. A photon is a spin 1 particle, but because it has no mass, the projection 0 is not allowed. It would correspond to a longitudinal photon. It's not possible, but no matter what, this is a spin 1, it's a vector field. So photon here, the gauge bosons which mediate the weak interactions and the strong interactions. The strong interactions, they are called the gluons. The gluons are spin 1 particles, and the graviton is a hypothetical particle related to the mediation of gravitational field by quanta. It is not discovered yet. Perhaps it's non-existent, but if it exists, it is supposed to have spin 2. All right, so gravitons, if they exist, they will have spin 2. And here for spin half, you can have electrons, protons, neutrinos, quarks, neutrons. Okay, 3 halves, 5 halves, composite particles. If you compose an odd number of half integers, you can have half spins. So there is a property which goes beyond the scope of what we are trying to talk about. So the addition of angular momentum, if you have two particles, you can do, if you have n particles, you can add particle 1 to 2, find out the resulting systems and add the next one, proceed that way. So the addition of angular momentum will produce something like this. The resulting J value will be between the modulus of J1 minus J2 to the sum of both. Okay, so if you add two electrons, they are spin half. You can have two possibilities: the total spin of two electrons, or the total angular momentum of a composite system of two electrons will be 1/2 minus 1/2, because you pick up this number here, which characterizes the spin of a particle, which gives you 0, or 1/2 plus 1/2, or 1, and it changes by one unity. If you have something like between 0 and 2, you will have 0, 1, 2. All right, but in this case, you have just 1. So if you add a particle of spin 1 and a particle of spin half, the composite particle would give you a particle of 1 minus 1/2, which would be 1/2, and 1 plus 1/2, which would be 3/2. So a composite system of 3 electrons, for instance, would produce something like this or something like this. Okay, but this is enough to know. There are composite systems, for instance, the nuclear spins of protons and neutrons, they combine. They are half integer particles, but when combined, you'll find out the total nuclear spin of that element, and it can be any number, any integer or half integer number. And of course, you can consider the total spin of an atom. You need to find out what happens between the electrons, and considering also the angular momentum, not only the intrinsic spin. And an atom can perhaps have a integer or half integer spin, but must follow the rules of angular momentum addition. All right, so this is a very important aspect. Just to remember, there are integer spins, half spins, particles, and they are produced by the representations of the rotation group. There are also uses of unitary groups in other contexts. So just let me finish with one example. It's very interesting because it started with non-abelian theories. So non-abelian theory, it's just a curiosity. It started with Young and Mills, 1954, I guess. If I'm not wrong, it's around that year. All right, and Young and Mills thought that the nucleons, which are neutrons and protons, just just for you to see that the general rules for rotations can be used in some abstract space, which is usually called isospace. Okay, it is not the space of coordinates, but you can define some space, some internal space. Some internal space also is a nomenclature used in internal space. Okay, and mix objects into another object, right? So neutrons and protons, call it N, call it P, right? And Young and Mills, the theory, the general theory is wrong by several reasons, but is the starting point for constructing non-abelian theories, which are today describe the standard model of elementary particles. The ideas here are revolutionary, and it started the revolution in particle physics, but they thought the following thing: the masses of the neutron and the proton are nearly the same. Okay, the electric charge, okay, here you have a particle of 0 electric charge, and the proton is a +1 in terms of the electron charge, is +1, the modulus of electron charge. They have distinct charges, but when interacting inside the nucleus, the electromagnetic interaction plays a secondary role because the strong interactions are very strong. So strong interactions are order of 1, so strong here, electromagnetic are order of 10 to the minus 2, right? 1 over 137, so the fine structure constant. But they thought they could mix these objects. So you would interpret as an isospin. It's not the true spin of the particles. So an isospin. Okay, you construct a polyspinor, but is a pseudo spinor because the particles have their internal spins. So this object internally, the function here is a internally here the function is depend on space, depend on the proper intrinsic spin, but you are looking only at the possibility of mixing protons and neutrons. And the Young and Mills, I don't remember if they put the neutron here and the proton here or in the reverse order. Okay, but it doesn't matter. It doesn't matter because you can do both ways. It doesn't matter if you properly define things. And notice that in this isospin, they use it also for the Pauli matrix, another notation. They use it the tau, tau x, tau y, tau z, but they are the Pauli matrices, just the Pauli matrices here. Okay, they are the Pauli 0, minus I 0, 1, 0, 0, minus 1. And this object here corresponds to something called the Nucleon wave function. All right, and this Nucleon wave function here, I don't know if you can see here what I'm writing, but notice that the electric charge would be represented by something like this: a density matrix plus the tau z matrix divided by 2. So if it's the 0 for the neutron and 1 for the proton here, if you have a proton, you have the charge 1. If you have a neutron, the eigenvalue here of this tau z matrix is sorry, minus 1 here, minus. So if you have a proton, you have a minus 1 for the eigenvalue, so the charge will be 1. It's a charge operator. And if you have a neutron, you have the eigenvalue plus 1, so 1 minus tau z, you'll have the charge operator defined that way. And the idea behind this is what that is that neutron and proton could not be distinguished. They are just a matter of viewpoint, and they get mixed inside the nucleus, and they change places. They are exchanged, and they are subjected to internal rotations. So in one point you could define neutron and proton as some probabilities here, and when the wave propagates, a proton can mix with the neutron and it rotates. So this object can be rotated, all right? But there are more to that. I just emphasized that the idea was original by Young and Mills, using polymatrices, rotations in an internal space, because inside the nucleus you could have some interactions like this. A proton, it emits a particle which is a meson, and it is converted to a neutron. In this meson here, of course, it's positively charged, because charge conservation must be always satisfied, must be ensured by something. Okay, so this character inside the nucleus of an atom, which corresponds to a proton changing its identity to a neutron, and a neutron could be transformed to a proton, they thought it as a possibility of rotating the state. Okay, so this is a total spin flip, but it's not a true spin, it's an isospin. Okay, but they need to consider some mediating particles, which are the mesons, and they would be massless, but when you measure the masses of these intermediate particles, they get a non-vanishing result for the mass, and the theory was fundamentally wrong because of that aspect. But special unitary groups right now are used to describe a lot of things in not only real space of coordinates, but you can consider internal spaces. So in electroweak theories, electroweak, you consider an SU2 group, but not related to the real spin. It is just because the electron with something called the left-handed electron mixed with the neutrino, which is a left-handed neutrino. They get mixed, and you can rotate what is an electron and what is a neutrino. They rotate. The probabilities are changed because of electroweak interactions. Also, you have an electron, it can be changed to a neutrino, but perhaps you need to emit a particle with negative charge. Okay, so electron can be converted to a neutrino electron. Okay, in this kind of interaction, which changes the identity of the particle, is represented, or is treated in a theory using some objects like this. Also in the chromodynamics, which describes the interaction between quarks. So this is called Gcd Quantum Chromodynamics. You use three charges, which are known as color charges, and the quark, say the up quark, can be in any state of charge: blue, red, and green. Or I guess they used an analogy with the RGB of colors. So RGB. nothing to do with the real colors we see with our eyes, but because these charges come in three different species, they called these charges red, green, and blue. It's distinct from the electric charge, which comes only with plus and minus, electrons or positrons, electrons or protons, plus and minus. For color charges, you have the red charge and the anti-red charge, which corresponds to something like a minus red charge, a green charge and minus green charge, a blue charge and an anti-blue charge. But these objects these objects can mix. So what is red, green, and blue in one point space, you can say in other space point, you can say no, this is red, is a mixture of red and green, and this is blue, and these matrices are 3 by 3. They can mix the quarks, and this quantum chromodynamics is described somehow by some internal space. It's not the real space, okay? It's not the coordinate space, some internal space which has three parameters. Sorry, in the case of quarks, I guess there are 8 parameters. So the parameter space is 8 dimensional, but is represented by this group of matrices 3 by 3. You can find out 8 matrices in this group. As a matter of fact, the number of generators for SUN SUN, the number are n squared minus 1. Therefore, you get a set of 8 matrices, distinct matrices, which correspond to 8 parameters. You can rotate around or along any of these axes. So you can think about existing axes. So the internal space has 8 distinct axes. And rotations here are unitary, special unitary matrices 3 by 3 in the case of quantum chromodynamics. But I guess I extended a little bit this discussion, and it's just some curiosities, all right? But what really matters for us is the possibility of representing the rotation group by the spin representations, so 0, half, the integer spins and the half integer spins. In next lectures, we will discuss a little bit more about the spin statistics theorem and second quantization using operator algebra of annihilation and creation operators. Hope you enjoyed it and you could understand at least the main aspects. And see you next time. Bye bye.